which of those compounds could match this spectra?
The top two.
The left two match. The right two don't match because we don't have an OH and we don't, have a carbon-oxygen double bond. Is there a difference between the left two structures? Yes. Does the, it's not a circle, what is it? It's an oxygen, it's lazy man's oxygen. Yeah. Okay. There is a significant difference between these two structures. Does that show up in the IR? Yes. Are you responsible for it? No. Okay. At best, you would hope to see the CO single bond. The CO single bond should show up about 1100. There's nothing there. So technically that epoxide, that second one, doesn't fit. Okay, but that's kind of in the fingerprint region, that's taking it above and beyond. Kind of makes sense? So multiple structures can match an individual IR. So a lot of times, or pretty much all the time, when we're looking at IR questions, what you are expected to do is not to find the correct answer. You are expected to find all of the wrong answers and not guess those. Next, what do we have? We have how many carbons? We have 4 unique carbons. 1, 2, 3, come on, pen. 3 and 4. What else can you tell me about these? These are all in our alkane, that says ane, region. And then this we don't really know. Okay. It is fine to admit you don't know something. Don't go through and say, well, the textbook listed there's 6 possible things that could be, so I'm going to write down all 6 possible things. The issue with that is the instant you move on to the next part of the problem, you forget that you wrote down all the possible things, and you now look back and think, oh, all of those things need to be in my structure. No. Okay? You wrote down the possibles. Okay? So don't write down possible things because you don't know. So pick the best one if you want to pick one, and work with that and put a question mark next to it. I would argue you should just put a question mark next to it. Okay. Next, what do we have? You and your numbers on this graph, Tristan. I don't know what's going on. Okay, so maybe I see what you're saying. You are referencing the blue peak. Mass spec. When we interpret our mass spec, we look for the peak furthest to the right, which I agree is 111. Right. We look for the tallest peak within the set of peaks that is furthest to the right, which is 110. Okay. That is now the molecular weight. Well, those people are not all me.
No, not you.
I say the same thing.
I blame Nate.
So that is your molecular weight. What else can we determine from that?
Formula.
I would argue the formula is kind of a one question, one-off thing on the exam. I wouldn't stress about that until probably the day of the exam. What do I have to do to get that formula? No nitrogen, bromine, chlorine, or iodine. No nitrogen because? Even. No bromine? No M plus 2. No chlorine? No M plus 2. No iodine? Too small. Right. You're trying to draw as quick a conclusion as possible about the information you've got and then immediately move on. Right. And then we've got this. We have 3 unique hydrogens as our first pass. Okay. Because of our range, we're looking at likely 2 alkanes. And then 1 I don't really know. Okay. And now I would pause for a moment. Everybody should be able to nail that down that fast. Okay. No questions asked. Everybody in the class needs to be able to do that. Okay. The biggest reason is everything after that point becomes exponentially more difficult to interpret, which means you will spend more time on it. This gave you information. With that information, you can eliminate answers. Don't work harder than you have to. Work only as hard as you need to. Okay? Identify the easiest information first. See if that gets you somewhere with your multiple choice. If it does, great. If it doesn't, then work harder. Okay? Yeah, it's not a bad mantra. It's also kind of lazy, but that's a good thing. Okay? Now what could we do? What's that? So the number of peaks within the signal, I would argue, is not what we should look at next. But maybe you're saying, jumping to that because you're missing something else. How many hydrogens show up? We're looking at the area underneath the signal. Okay? Also known as, those of us in calculus, integration. The integration value does not give us the number of hydrogens. It gives us the ratio of our hydrogens. Okay? So we have to be careful when looking at our integration. Okay? Sometimes we'll be given that data and told 3 hydrogens. Well, if you're told that, then it's probably 3 hydrogens. Okay? If it just says 3, that's not saying 3 hydrogens. That's saying the area there is 3 times the size of something else. Okay? So, where's the integration information given on this? So we listed it in purple. Anybody see it up there? Where did you see 372? Oh, I see what you're looking at. No, that's the code for the unknown. Not a bad guess. And I have hidden them on there. I'm actually wondering if I hid it on there. I don't think I did. Okay. The final exam does not give you the integration information. I don't understand why. Okay, that makes no educational sense to me. Okay. The area underneath the curve is dictated based on what 2 pieces of information? The width of the peak and the height of the peak. When we're looking at most of our HNMR, look at the width. How much does the width change? And it's not the best, but is it changing really that much? Not really. Okay, what is changing? The height. So what we can attempt to do is draw conclusions based off of the height. Okay? Very hand-wavy, very sketchy. It kind of works. Okay? Based off of that information, what do you think you see for integration?
1 in the center, 2 on the outside, and 3.
Okay. I'm hearing a 1, 2, and a 3. I'm hearing a 2, 2, 3. Why 2, 2, 3? I would argue that you have a wider section here than this one. The height difference isn't all that large, but that extra width is probably stacking it, and I think 2, 2, 3 makes sense. Okay. It is so dicey to just look at the height of the signal. I mean, it is a horrible, horrible method. Okay? And it is something you would never, ever do, because when you put it into the instrument almost always instantly spits out, by default, the integration information. You don't find spectra that don't give you integration information. It doesn't exist. Okay. I didn't record my mild rant. It goes out into the whole world. I don't want the whole world of other people to hear that. Okay. So we have 3, 2, 2. What does that mean to us? Reading from left to right, the signal at roughly 2 corresponds to 2 hydrogens. Okay. Do I know what those 2 hydrogens are connected to? We don't know. The chemical shift is what tells us information about what it's bound to. You said it was a question mark. So I have a question mark bound to 2 hydrogens. Okay. Could it be oxygen? Not possibly. Does not depend. Cannot be oxygen. Why? We don't even need to get into neighboring to figure that out, but yes, you're right there. There's an interesting point. We didn't see an OH in the IR. That also works. The hiding feature is dealing with multiplicity. That's the next step. We have another piece of information here. Just looking at this to say that can't be oxygen. Because remember, back in Unit 1, I told you that you should memorize all of the common bonding patterns for your compounds so that when you drew out structures, you would know, oh, that works, that doesn't work. One of them for oxygen to be neutral, since we're looking at neutral compounds, it can only have 2 bonds. If 2 bonds are to hydrogen, I have water, and I have no way to connect that to any other part of my structure. It can't be oxygen. Could it be nitrogen?
No.
Yes, just based off of the NMR, yes. I don't have any evidence to tell me it's not nitrogen yet. Okay. If I want to bring in mass spec, I can potentially say I don't have nitrogen because of the mass spec. Okay. So I really don't have a way to eliminate it yet. How about the next piece? Okay, we said that was a carbon. It's still bound to 2 hydrogens. I like to show the hanging bonds. Next piece. Carbon to 3 hydrogens. And then that one hanging bond. Right. We could then move to the multiplicity, also known as the splitting. It's the number of peaks seen for each of those. It's in reference or gives us information about the neighbors. So for our leftmost signal, how many peaks do we have? 3 peaks, which means 2 neighbors. Okay, that gives us 2 pieces of information. 1, there's 2 neighbors. 2, I know what the question mark is. What is the question mark? It must be carbon because it has nothing to do with the number of bonds. Because it has 2 neighbors. By sheer fact that it's splitting, I know it can't be nitrogen or oxygen, because nitrogen and oxygen hide their hydrogens. Okay? Because of this, I had 2 neighbors. That means I move 1 bond. If that was anything other than carbon, it would hide those hydrogens, so it must be carbon. Hydrogen? Come on. Hydrogen. We've now drawn that piece. Okay? That was 15 minutes, which is roughly 10 minutes longer than I wanted to spend. So finish it. Come Monday, you should have a final structure that matches all 4 spectra. Okay? Now we got a little bit of hopscotch to do. We're jumping all over the place. This is because what I'm trying to do is get the hard material done with today so that Monday it's more kind of review, practice, and nomenclature. Nomenclature is just a rule. You just have to know the rule. Okay? So spending time talking about it today doesn't make sense. So what we'll look at today is some more of the kind of harder aspects. We'll kind of try to skip through some of the just facts and get into kind of the nitty-gritty details. Okay? So, big summary. That whole flow chart, you need to be able to do. Given 2 structures, you need to identify their relationships. This has all of the relationships you are responsible for. Okay? And if you have the PowerPoints printed out, I apologize. This literally does skip all over the place. Okay? So you need to be able to follow this flow chart to look at those comparisons. Where we ended Monday was now taking a look at specific examples of these. So if we look at diastereomers and we look at their physical properties, because the change of shape is there, okay, because that's what happens when we look at diastereomers. We have that change in shape. That changes how those molecules stack, which then means we get different physical properties, different melting points, different solubilities. Which is great, because if they have all those different features, then they can separate away from each other. If I have a liquid that boils at 100 degrees Celsius, and a liquid that boils at 70 degrees Celsius. How can I separate them away from each other? What?
Boil them at different temperatures.
Just boil them. What's going to come off? What's going to boil first? The 70 degrees Celsius one. And we have what is commonly known as spring break. Feel free to take a look at that one. It's a little bit convoluted. Work your way through that. Okay, most diastereomeric pairs we can separate because they have significantly different properties. Okay, to be able to go through and identify those compounds, okay, we have to go through and isolate them first through a separation technique, and then we can identify them using something like melting point, or say spectroscopy. Okay. The big issue comes down to enantiomers. Because enantiomers are organized roughly the same, right, just mirrored of each other, they stack with like molecules identically. Which then means the forces within the within one enantiomer is the same as the forces within another enantiomer. Okay? Which means the melting points, when I look at the two pure samples, are identical. Which then means if I had a mixture of them and I tried to boil one off before the other, I get them both coming off at the exact same time. I can't separate them. And that's because when we're looking at physical properties, that is an achiral system. The only way we can distinguish those two structures is by comparing them to a chiral system. Okay? And what we looked at, we've got three potential categories or three potential examples up here. Okay? Naproxen. You have a liver toxin and an anti-inflammatory. Okay? Generally a good idea for the drug manufacturers to make sure that when they make it, they remove the liver toxin. Okay? Sometimes they don't because of that cost benefit. Okay? It costs us $5,000 to do that, and we only kill 2 people's livers. We'll accept the $5,000 cost. Or we'll accept the 2 people's dead livers. Okay? Yes, that kind of calculation is cold and hard, and it is not scientists that are making that decision, just for the record. That is not science, that is business. So do not blame scientists for some crappy business decisions, because it is the business people screwing us over. Yes?
Wait, so how do they separate it?
So that's an interesting question, okay? Which gets us to the next part. If all of their phases are the same, how can we possibly separate? Well, how did we detect that they were different? Well, we ingested and said, oh, our body separated it. And in the process of separating it, it killed us. Ideally, we have a better option than that. Okay? Why can our body tell the difference? Our body is chiral. Okay? So to get or to come up with a way to separate these, I need to introduce them to a chiral method or a chiral separating system. Okay? And that is not easy. Because the whole point or the whole process, we will likely make these, and in the process of making them, we make both. Well, how do we make only one so we can then separate? Which comes first, chicken or the egg? Okay? So how can we go through and separate these? Number one, don't make them. That's the easiest way to avoid this. Design your experiment so that you don't make both enantiomers. You only make one. Okay? So that means you have to choose your reagents very carefully to ensure that you don't get both. Okay? And as we'll continue to find through the semester and next semester, that is not very easy. Okay? Number two, separate them on a chiral medium. Okay? In lab this week, we looked at column chromatography. Okay? That is a medium. That is an achiral medium because it's just sand. Sand has no chirality associated with it. If we, instead of using just sand, but embed or physically attach to that sand molecule something that is chiral, now when I do the column chromatography, the medium will differentiate between the two compounds. But that again requires I have a pure chiral thing to put on it. Okay? The next one is continue to react them. I make both. Oh crap, I've got them both, but now I'm going to react them again. But I'm going to react them with a chirally pure compound. Okay? So here's the classic example. The two structures shown on the left are enantiomers of each other. They are not the same structure. But what I will react them with is tartaric acid. Okay? Tartaric acid, optically pure. So now what happens when I do a reaction? I'll get one salt where I have the wedged nitrogen, and I'll have the R tartaric acid. Okay? R is just a label for this moment. I'll take the dashed one, and that's still going to be the R tartaric acid, because that's all I added here. Right? What is the relationship now between the top and the bottom? And if you've seen this lecture before, keep your mouth shut. These are enantiomers. I take enantiomers and react them with one species, a pure form. Okay? What is now the relationship between the products? It's going to be kind of challenging to look at. Okay, so let's go through and establish. Say that top one, somewhat arbitrarily, is R, the bottom one, S. When I go through and take a look at my product, what do I have? The top one would be, oh, don't you die on me now. R, R, R.
What is R?
R is the label that we're referencing for each of those positions. Okay? And we were told the tartaric acid was RR. Okay? So the result I get out of that top one is 3 R's. Okay? That R is a way to say, well, is it a wedged or a dashed, effectively? What do I get out of the bottom one? I get S, RR. What is the relationship between those? R and S are opposites of each other, right? So they would be mirror images, which would make them enantiomers, right? So that's a mirror. What is RR? The same. What is RR? The same. What is the relationship between two structures when I only mirror one chiral atom? Diastereomers. What is special now about these two products? They have different physical properties. I can separate them now. Okay? Easy process? Hell no. That's why we go back to rule 1. Don't do it. Okay? Last part of this, okay, that should say 4. You screwed up. You can't differentiate them. You can't separate them. At least report that you screwed up. Okay? We will report that as what is known as the excess of our enantiomer. Which one of those do we have in a larger concentration than the other? Okay? So to calculate that, the enantiomeric excess is the percent of the highest one minus the percent of the lowest one. Cool. I now have an excess. Theoretically, that excess should be what value? It should be 100% because I only have one. What is the worst value we could possibly get? 0, because I have equal concentrations of both enantiomers. Anywhere in between says I now have a variation of more of one than the other. Okay? So that's what we would end up reporting for it.
Can you not fix batches like that?
It comes down to doing those 2 and 3. And yes, you can theoretically do it. It's not easy. Okay? So then the next question might be, well, to calculate the enantiomeric excess, what do I need to know? I need to know how much I have of each. How do I know how much I have of each? That sounds like an experimental technique. We talked about any experimental techniques yet? No. How do we verify our percentages? What we found, this goes all the way back to Pasteur when he was looking at tartaric acid and he manually separated the chiral molecules. He noticed that light interacts with different molecules or the different enantiomers differently. When light hits one enantiomer, it rotates, say, to the left. If it hits the other enantiomer, it rotates to the right, in equal distance. So this means I can now look at a sample with light and say, well, which way did you rotate the light? I now have an idea of which one I have in excess or not. This is looking at specific rotation, okay, or optical activity. Because we now have a left and right associated with this, we can label our enantiomers as levorotatory or dextrorotatory. Okay? The issue with labeling them levorotatory and dextrorotatory, those are really big words. So we can call them instead L and D. What type of letters did I just use?
Lowercase.
Lowercase. I did not use capital L and D because capital L and D means something else entirely different. They must be lowercase. Yeah, I didn't invent it. Okay. The other option is we could then reference the direction the light moved. Okay. Either being negative direction or positive direction. So we now have two ways to label our enantiomers as either L and D or minus and plus. L is by definition minus, D is by definition positive. Okay. So I can use this to help me determine what I have in excess. Okay. There's a little note there about not the same as R and S. We'll get back to R and S on whatever it is, Monday. Okay. So how do we use this? Well, in an individual sample, okay, what's happening is the light comes in, okay, and the very first thing we have to do is make sure that the light, we can see that the light rotates. Okay, what's the issue with light? Is light polarized? No. This is why we have polarized glasses, because if light was polarized and you put on polarized glasses, what happens? One of two things. Nothing changes. You get the exact same light intensity as you saw before. Or two, you see nothing. Not no change, you see nothing. Literally no light. Okay? You might say, well, that seems kind of weird. I don't believe Mike. Does anybody have polarized glasses? Does anybody have two polarized glasses? Take your polarized glasses and turn them. When you hit 90 degrees, guess what happens?
Nothing.
All the light is blocked out. Because light is not naturally polarized, but when passed through a filter of polarized glasses, it is now polarized. If I put it up to another filter, I can then cancel out that polarization. And I can completely cancel all light passing through. That's what we're doing with this. We take a filter that polarizes light. So now the light is only gained, say, one up and down. That light then goes up to our sample. Okay, and so our sample's chilling in here. If we have R, what happens? The light hits the R molecule, and what does it do? Rotates to the right. As it continues to pass through the sample, it hits another R molecule, and it keeps rotating to the right. I can't say R. That's bad. I shouldn't be doing that. Let's say the D. Sorry. Okay. Hits D, rotates to the right. Hits another D. What happens? Keeps rotating right. Another D. Keeps rotating right. It was a mixture. It hits an L. It rotates an equal and opposite direction, left. Right? What happens to our signal or the amount of rotation? Well, a couple things are going to determine that. We will have the observed rotation, and that observed rotation is going to be dependent on the amount of particles present, also known as the concentration. Okay? Not only the concentration, but what if I make that tube stupidly long? Okay? If I look at it from the end, do I see a different color than if I look at it from the side? Yeah, that's because of concentration dependence. So we also encounter this L value, which is our path length. Okay? So what we do is standardize our calculation based off of concentration and path length so that what we report is now consistent across the board. Anytime someone looks at this compound, it has this specific rotation. It is a physical property of that compound. Okay? We can then report that. Okay? So we can run through a whole bunch of nasty calculations. It's super exciting, all that fun stuff. Okay? Ultimately, what's going to come down to it is, what do we ask? So if we're going to look at optical activity, the common way to ask this is, which of the following show optical activity? Okay? I forgot to scrub the R versus S stuff out. So let's just make that D. So what do you guys think for that first one? Do you think it would have optical activity if it was all the D enantiomer? Yes. If there's only the D enantiomer, it rotates light to the right, we see optical activity. What about a meso compound? That gets a little bit tricky. A meso compound says it has an internal mirror plane. One of those atoms will be D, and the other chiral atom will be L, which is officially R. We'll go back to R and S. So the molecule gets hit by light. The first chiral atom rotates it to the right. What happens when it hits the second? Rotates it right back to 0. And we see what for our optical activity? Nothing. So a meso compound results in no optical activity. Let's just say no. And this one will say yes. How about if we had a mixture of enantiomers? Ooh, that could be dicey. Because if it sees one, it rotates to the right. Sees the other, it rotates to the left. That would cancel it out, right? Okay. What's that?
It says it's 3 to 1, so it go left.
But it says it's 3 to 1. Which means in this case, do I have optical activity? Yes. And I would expect that optical activity to lead me to which enantiomer? The L, based off of how the data was written for you here. How about the next one? No, because even ratio. Last one, a mixture, well, second to last one, because I got another word to add up there. A mixture that has 0% enantiomeric excess. What did we say enantiomeric excess was? Percent D minus our percent L, or vice versa. If I get 0, what does that mean? They're exactly the same. That is the previous answer, which means no optical activity. Okay? So it's a way of experimentally determining, do we have a chiral atom in our molecule? Officially, it's do we have a chiral molecule, but we can use it to just look at the chiral atoms. Kind of makes sense? The case for those last two is so common that we end up inventing a new word for it. We can call it racemic. Okay? That would be the adjective. We can call it a racemate, which would be the noun. Okay? So you will see varying versions of racemic or racemate. They're both referring to the same thing. We have an equal mixture of those two things. Okay? So we get 0 optical activity.
So you can't separate.
This has nothing to do with separation. This just says, what do we have?
But you
This is an
won't see-
identification.
You won't see.
You will not see optical activity. Okay? Why is not seeing optical activity potentially misleading? Would hexane generate optical activity? No. It's an achiral molecule. What optical activity determines is, do we have chirality? Okay? What's misleading about not seeing optical activity? Well, hexane is achiral. We wouldn't expect to see it. Are enantiomers chiral? Yes. And yet, we don't see optical activity if we have a perfect mixture. Okay? Kind of makes sense? So we have to be a little bit careful with our analysis within optical activity and not to get too overexcited about it. Okay? Which then brings us to the next fun part. We can take that calculation and we can exactly determine the percent or the percent of each of our enantiomers present, either D or L. Okay? And this comes from definitions of what the enantiomeric excess is. Number one, we already established the percent of the highest enantiomer minus the percent of the lowest enantiomer. The next definition that comes out comes from the optical activity. We'll look at the ratio of whatever our unknown is, and we'll compare that back to a standard. So the optical activity of your mixture in comparison to the optical activity of the pure enantiomer. Divide that, multiply by 100, you also have the enantiomeric excess. Okay. So we could be given the question, though you won't, specific rotation of iodobutane is plus 15.9. Determine the percent composition of an enantiomeric excess of iodobutane if the specific rotation of the mixture is negative 3.18. Okay. So what I'm asking for is what is the percent of the positive, what is the percent of the negative? Okay. Which might be easier if we switch it to percent of the D versus the percent of the L. You might say, well, that's impossible to figure out. All the information you need is given to you. There's a couple big things that come out. S and R and plus and minus are opposites and equal opposites. If you are told that the pure S is plus 15.9, then what is the pure R? Negative 15.9. If our mixture is negative, what does that mean I have more of? The S or the R? The R. There's a potential for multiple choice answer without actually doing any calculations. Lovely. Okay. The next part where we might have to get into a calculation, the percent of S plus the percent of R. And this is the one that everybody seems to miss. What does that equal?
1.
Close, not 0. It says percents. 100%. There's only two things. There's only two options. Okay? Which means if I know S is 50%, what is the R? 50%. It has to add to 100%. With those two bits of information, I can then go through and determine the percent of S and R plus or minus, however you want to label it. Okay? I'm not a fan of numbers. I also think it's kind of a waste of time to do these kind of calculations. That said, I do expect you to have at least attempted to see it, which is why I posted a video to Canvas. If you want to look at that calculation, by all means go ahead. But my responsibility for saying I've shown you that calculation is now done because I've given it to you. I won't ask that question. Kind of, sort of? So, hopscotching. Back to our UV vis. So when we talked about UV vis spectroscopy, we were referencing pi bonds. Pi bonds are what are absorbing our ultraviolet light. They're the highest energy electrons, and it is those electrons jumping to the lowest unoccupied molecular orbital. This is the HOMO to LUMO gap. Right? As we add more double bonds, right, we're going to add more molecular orbitals. However, we can't continue to increase the energy. In fact, if anything, when we add more double bonds, it actually decreases a little bit. Which means what happens to the gap between the HOMO and the LUMO? It decreases. It gets smaller. That means the more double bonds I add into my system, the smaller that gap becomes, which then means what happens to the wavelength when I see a signal in my ultraviolet light. The wavelength increases because I'm seeing a smaller energy gap. Wavelength and energy are inversely related. There's our answer. So let's take a look at a couple big examples. Compare the first two. Look at the structures. What's the difference between them? We could go with one symmetrical, yeah. Do they have pi bonds? Yeah. Yes. Okay. The pi bond is what gets excited. Are those pi bonds particularly different in energy? Yeah. They have some difference in energy, but it's not a huge difference. Okay. You have one carbon on there versus no carbons as a substituent. So if there's not a large difference in energy, what should we expect to happen to the HOMO-LUMO gap? It shouldn't change. Look at the value. Less than 160 to 177. It's not that far off. Okay? but maybe all those extra carbons are making that big difference. So let's go ahead and compare that. Twerps. Let's compare it down to this one, where we have another 1 carbon, or 1 pi bond, but we've now added a bunch more carbons. What happened to the frequency? Or the wavelength? It went up. By a lot? Why not? It's the same energy. We're still looking at a single pi bond. It may have changed its energy a little bit, but it's not significant enough to change the wavelength to excite between the HOMO and the LUMO. What happens when we add another double bond? Oh, we'd expect a bigger jump now because we have 2 double bonds. And yet what happened? 177 to 178. Did it change much? Why not? I may have more double bonds, but what is the energy of each of those double bonds? They're all the same. Which then means no difference in the HOMO-LUMO gap. What happens if I change the location of that second double bond? I've now jumped to 223. Whoops, went from the wrong one. Went from 178 to 223. Is that a significant jump? Yeah, we're looking at a 40 nanometer jump there. Why is it all of a sudden jumping? We still have 2 double bonds. The bonds are closer to each other. Why does that matter? I was hoping they gave us a different one. They didn't. What do we now have? Resonance. Remember when I said the answer to why is typically resonance? Guess what? Why are we seeing this change now? Resonance. The pi bonds have now dropped significantly in energy because resonance. The electrons are now allowed to move not just between 2 carbons, but across 4 carbons. I've given them more space to move, which means they are happier, lower in energy. That lower in energy transition means they get a higher wavelength, hence the large jump. Okay? We can continue to make those comparisons by moving through it. Right, what happens if we add 4 double bonds? We jump up to 290. Okay? So the more resonance we've got, the smaller and smaller that HOMO and LUMO gap becomes, which means the longer the wavelength. So really all UV-Vis spectroscopy is giving you is, do you have resonance? If you've got a really large wavelength, the answer is yes. If you have a very small wavelength, the answer is no. Right? Why does this become particularly relevant? How do you see compound known as retinol coming from beta carotene? What does beta carotene have a lot of? Pi bonds. What's happening when we see? The light excites a pi bond, allowing it to rotate. When it rotates, we change the structure. That structural change sends a signal to our brain saying that is color. Acknowledge. That's how we see. Which is kind of neat. Right? It's just the rotation about a double bond, which is happening because of ultraviolet light absorption. Okay? So, effective conjugation. As we add more double bonds, the gap between the HOMO and LUMO gets smaller. The smaller that gap, that means less energy, which means higher wavelength. More resonance, higher wavelength. And that's really about it when it comes to UV-Vis. Questions about that? Okay. Look at that. Almost a big another jump. We now move into the IR region. So we started at ultraviolet energy and we've now dropped out of visible energy and into infrared light. IR light is not enough energy to cause our electrons to move. So they stay in their orbitals. However, it is enough energy to cause things to move. Okay? If we froze this room, you would all probably huddle up and get real close and tight to each other so we could all stay warm. But what happens is we heat up the room. You get further and further away from each other because you want to get rid of some of that energy. It's too hot. Okay? So you start to move and expand out a little bit more. Okay? That analogy only works so far because eventually we just get hot and pass out. But atoms don't pass out. Okay? So what's happening with our molecule? Well, that energy comes in and it causes a bond to vibrate. That's it. Okay? And we'll do the same thing as we're doing with ultraviolet light. We're just scanning all those possible energies and saying, did the molecule start to vibrate? If it did start to vibrate, I now have a signal. I then record that signal, and I can then compare that signal back to standards. Okay? How do we report that signal? Okay, well, since you guys have already been analyzing IR, it's 4,000 to 400 typical ranges for inverse centimeters. What is inverse centimeter typically? It's not wavelength. Wavelength would be centimeters. It's a frequency or a period. Okay? Because we're calculating it based off of actually the wavelength and not the number of cycles, okay? We can't call it frequency, we can't call it wavelength. It's really the inverse wavelength, which we end up calling the wave number. Why? Because we can. Okay? So we'll refer to it as our wave number. We still have this energy to frequency relationship, which we have to remember and maintain. So what happens when we look at our spectra? Okay, well, it's causing a bond to vibrate. Okay, our bonds, depending on who you had as an instructor, are really just two atoms with something connecting them, right? What's that something connecting them? Electrons being shared between them. Can one atom move away from the other atom? Yeah, it absolutely can. Okay? Eventually, it moves so far away that the bonds break. So they can absolutely move. That's how we break bonds. Okay? But what happens if I move it just a little bit far away, but not far enough to break the bond? It starts to stretch it. Does the atom want to be stretched? No, it wants those electrons to share evenly. It's starting to get too far away from the electrons. So what does it immediately try to do? Compress back down. Okay? And eventually, if I give it enough energy, what happens? It bounces back and forth, and we've got what's known as a bond stretch, or a stretching vibration. The energy required to cause that bond to stretch is now our signal that we're looking at. We're looking at IR, almost everything that we're concerned about are our stretches. Are there other types of vibration? Yeah, I could have just as easily done kind of a rocking action like this, okay? Like a bend. What if I added in a third atom? Say my chest is a third atom and my fists are another atoms. Well, I could still stretch. That would be an asymmetric stretch. Or symmetric stretch. All of those are bond vibrations that do show up in the IR signal, or our IR frequency. Okay? So we are sort of officially responsible for acknowledging that, though the only thing we really analyze are the stretches. Okay? What things are going to affect the energy of that stretch? Symmetry will come into play. There's other stuff. It'd be nice if I had a spring.
So is the bending?
No, we're just talking about the stretch. What's going to make it harder or easier for me to move my hands like this? Someone said pi bond. What does a pi bond do? Strengthens the bond. So instead of me just moving my hands with nothing connecting them, I could put in a really strong spring, and it'd be like... Okay? That's going to change the energy. If that changes the energy, guess what happens? I see a new signal. So if I change the type of bond, it changes the energy at which I see a signal in my IR. What else could change that energy? What if we change the atom? What changes? The weight of each of those. Which then means It's going to require more energy to cause that atom to move, or less energy to cause that atom to move. Which means when I look at these vibrations, I can say that particular energy for that vibration corresponds to hydrogen and oxygen, or hydrogen and carbon, or hydrogen and carbon where the carbon is sp3 hybridized, because an sp3 hybrid carbon has a different molecular orbital than an sp2. Right? All of those things affect the energy of that bond. How are you expected to be able to look at a value and say, oh, that's what that is? You aren't. Somebody else went through and tabulated that all for you. So what you have to do is look at it and say, does that match what somebody else told me the answer is supposed to be? Does it? Yes, that's what it is. Does it not? Then don't tell me it's that. That's what you're doing. Okay? So I liken IR spectroscopy. Maybe you had this as little kids. You had those little toy box things, the little shape cutouts on the top, like the little plus, the star, the circle, the square. And you take the circle block and you put it in the circle hole and it fits in. But you take the circle block and you try and put it in the star hole, it doesn't fit. That's IR spectroscopy. Okay? Does the shape match? If it matches, then it's probably that signal. If it doesn't match, don't tell me it's that signal. Okay? Stop trying to fit square pegs in star holes. It doesn't work. Okay? So, stretching frequencies. Let's take a look. What happens as we transition from hydrogen to deuterium? What happens to the deuterium? Hydrogen and deuterium are exactly the same. Deuterium is heavier. What happened to the frequency? It decreased. How is frequency related to energy? Frequency is directly related to energy. So we drop in energy to cause it to move. Wavelength is inversely related. What happens when we go from hydrogen to carbon? Well, now we've really jumped in the mass. What happens? It decreases a lot. So as we change the mass for an individual bond type, we see the frequency decrease because it requires less energy to cause that bond to vibrate. Okay? What happens as we move to stronger bonds? Single, double, triple. Okay? As a stronger bond comes up, what happens to our frequency? It goes up because I got to put a whole hell of a lot more energy into that to get it to bend or to stretch. So we're seeing the frequency go up with a stronger bond. Okay? You can then go through and compare other situations, but for the most part, what you need to recognize is that your frequency increases with increasing bond energy. That's the biggest one. The mass one I wouldn't worry about. Okay? But the energy of your bond has a drastic effect on what you can detect. Okay? The next part, okay, this is a nice little nuance, which is particularly relevant for the assignment I gave you to do over the weekend for Monday. Okay? IR detects based off of bond dipoles. Okay? If I take that bond, it's now stretching back and forth. The only reason I can tell it's stretched or not stretched is because I'm getting the positive and the negative end further from each other or closer to each other. That's how I detect. What if I don't have a positive and a negative end? Can I tell that it's stretching? No. Which means what do I see in the IR? Nothing. Okay? So when we're looking at our structures and our molecules and our bonds for IR, only bonds that have dipole moments are IR active. Okay? Which is most of them. Anytime we have different atoms attached to each other, we have at least a small dipole moment, and they are IR active. What if we have a bond that has a zero dipole moment? Well, then that means they're IR inactive. I can't see them. When would I have a bond with a zero dipole moment? Same to same. Okay, so I could look at carbon to carbon with a zero dipole moment. But the instant I add another carbon, now I have a dipole moment. Okay? So I have to be perfectly symmetric. So molecules that are symmetric run into lots of issues with IR because we start to lose those signals. even if we would expect and predict to see them, they disappear from our spectra because of that symmetry. The classic example, carbon triple bond carbon. Because I know you've all been studying IR. Where does the carbon triple bond carbon show up?
22.
About 2200. It's a nice bond to show up or have in your structure because the only thing that shows up in that range is a triple bond. Okay? And typically it's barren. So you can look at a spectrum and say, oh, no triple bond. But what happens if I switch this to now this compound? It's now symmetric, which means what happens to that triple bond signal? IR inactive, it completely disappears. When I go to interpret the IR, I do not see a triple bond. Huh. Your major regions. This kind of lists it out kind of neatly. Got a bunch of color coding within it. I would argue that what you should be looking... Oh, God, yeah, I forgot about that. This is very typically how IR gets taught, particularly by old school chemists. This is how actually I learned IR. I went into the library because I didn't believe them that all that was there was this. So I said, there's got to be something else because I want more out of it. And so I went to the library and found it's not just... This is just a page. This is a page of probably 3,000 or 4,000 pages like this that goes through and evaluates all the possible stretching and bending frequencies. I got so good at looking at IR, I could come up with a structure from the IR. Okay? Don't do that. It's not worth your time. Okay? But you could theoretically. Okay? So what do I expect you to get out of it? Okay? Your main solving region is 1600 to 3500. What does IR give you information about? Bonds. Okay? Bonds, and that is it. So one of my biggest pet peeves is that someone will come through and they'll tell me, oh, the IR said that I had the CO2H. And they'll tell me that because they looked up a table that said CO2H shows up there. The table did not say CO2H showed up there. What it said was the OH showed up there. Because OH is a bond. What is CO2H? A lot more than one bond. All of those bonds are not showing up at the same value. They show up at different values. So what you should be doing within the IR is identify all the bonds. If you have multiple types of bonds, say you see a carbon-oxygen double bond and an oxygen-hydrogen single bond, you can then say, I bet those two are next to each other, in which case I have the carboxylic acid. Okay? You're drawing conclusions from your analysis. You're not making conclusions in your analysis. Okay? The only reason I complain about that is because, again, you will overanalyze. Okay? When it comes to what you must strictly have memorized, this is the list. You need to know where the OH is, the NH, the CHSP2, the CHSP3. Your triple bond, notice I did not specify the atom attached to the carbon because it could be carbon or nitrogen. They both show up in about the same place. And then carbon-oxygen double bonds.
What about carbon double bonded to carbon?
Carbon double bonded to carbon does also show up, but if you have a carbon double bonded to carbon, you probably also have a carbon bound to hydrogen where the carbon is sp2 hybridized, which is a hell of a lot easier to see than the carbon double bond carbon. Okay? So it comes down to level of difficulty. These get you kind of to the gist of what you need for your structural analysis very, very quickly. Okay? If you wanted to, say, add some more information and you wanted to include the carbon-carbon double bond, yes, there are alternate lists. Notice that we have an OH. That OH is different from the previous one because the previous one says the OH shows up where? 33 to 35. This one says it shows up. Why would it show up in a different location? It's near a C double bonded O. Well, why would that matter? what is the difference between this OH and this OH bond?
One's carboxylic acid, one's not.
One's an acid, which means that bond is going to break. Why would a bond break? Which bonds are more likely to break? The weaker ones. In a carboxylic acid, the OH bond is weaker than in an alcohol. What happens if our bond becomes weaker? Lower frequencies. Why did we shift for the OH? Because it's a weaker bond. Okay? So some analysis that we just went through does tie back to this. Do you need that analysis? No, you can just memorize the crap out of it. Right? But it works. Kind of make sense? Notice the NH, I've added some extra information here. 2 peaks means primary, 1 peak, or sorry, 2 peaks means primary, 1 peak means secondary. Primary means it is connected to 1 carbon. Secondary means it is connected to 2 carbons. Okay? That's what it's referencing. CHSP3, or sorry, CHSP shows up at a little bit higher frequency. Okay? Or higher frequency. Your CH for an aldehyde shows up at a lower one. So it's nailing down some kind of nuanced specifics within IR. And you might say, well, don't a lot of these things kind of overlap? Yes, they do, which is why it's not just looking at the number, it's the shape of the signal. How do you know what the shape of the signal looks like? You need to practice. That's how you'll recognize these peak shapes. Okay? This is why, when was the spectroscopy assigned?
2 weeks ago.
A hell of a long time ago, so that you spent time practicing it. If you are just now looking at IR, I'm really sorry to tell you the next week is going to be horrible for you. Absolutely awful. Okay? Even if you've been looking at it, it's probably going to be awful. Okay? You need to be practicing this. Sample IR.
Which one was the better list in that first one?
So I had 2 lists. Bare minimum, nuts and bolts, you need to know it. What's this list?
It's more useful. We're really
Mike's BA list?
It's your bad.
There we go. That's the word. I won't say it. Yes, that is you are paying attention. You're going to destroy the exam when it comes to IR. And you've memorized those. Okay? Those are not required. They become insanely useful if you have them memorized. So, 5 seconds. What do you got?
CHSP3.
We have a CHSP3 and we have a carbonyl. That was pretty good. CHSP3 and a carbon-oxygen double bond. Okay. A lot of people will get tripped up by this signal here, and I don't blame you. Okay. It doesn't really match any of the peak shapes. Okay. Some people will refer to it as an NH. Okay. It still doesn't match the NH signal very well. What it's coming down to, where is this peak showing up? Right at about 3,400. This is inverse of energy. Okay, so what happens if I double the energy? What would happen to the signal? It halves. What is half of 3,400? It's the C double bond O. Carbonyls are such a massive dipole that even at 3,400, what they will do is absorb 2 photons of light to cause them to vibrate. They don't do it a lot, which is why that signal at 3,400 is very weak. But they do it enough that we can see it. It is what is known as the carbon-oxygen overtone. Okay? because it's a doubling effect. Do you need to know that? No, but it's a nuance within IR that if you study it enough, you recognize the patterns. Next one, 5 seconds. Time's up. Looks like we had it. We had the OH, we had the CHSP3. How do you know you don't have SP2?
Because it's below 2000.
It can be very hard to see the difference between the CHSP2 and the SP3 because it all comes down to how well you can draw a straight line off of the 3000. So what I would argue is don't draw a straight line. Get a second piece of paper, okay, and make sure you're squared. You will always have the x-axis. Line your paper up along that axis, match it up to that 3000. Anything that's not covered is CHSP2. Okay? The rest of it largely shows up in the fingerprint region. Probably not worth anything over there. Go.
CSP2,
CHSP2. This is your CHSP3. Probably looking at carbon-carbon double bonds. Those of you that have had some experience probably are tying both of these together to then say we have an aromatic ring. But aromatic wasn't on my list. I know. Because an aromatic structure is not a bond. It is multiple bonds. By combining multiple pieces of information, you can then suggest you have an aromatic structure.
That carbon-carbon double bond could have been a carbon bond too. So
No, would not be a carbonyl bond. Carbon-oxygen double bond shows up where? 1700. The lowest it'll hit is 1650. To get it to 1650, we have to do lots of weakening things to the carbonyl. What could we do to weaken a carbon-oxygen double bond? The answer to all questions in organic chemistry. Resonance. If we have a carbonyl structure that has resonance, that is going to weaken the carbonyl. That will cause it to slide lower. Very typically, your carbonyl is 1700 to 1750 range. Okay. Another little pet peeve. If you circle and tell me it's SP2 and SP3, I'm going to lose my mind. Why?
some carbon down to an H.
What does IR show you? A bond. What is SP2? A hybridization for an atom. That is not a bond. You will lose points for that. Okay. Make sure it is specified as a bond. You should specify the hybridization, yes. Looks like, oh, we get one more. Carbonyl. I'll admit that one actually looks kind of hard for me to line up.
Could that one be SP?
Probably CHSP3s and no SP2. Okay, without getting a ruler out there to line that up perfectly, it's hard to see. Okay? That's how fast your IR needs to be. Mass spec. Mass spec is fun because you literally take your particle, we put it into a detector. So probe, that's our sample. We spit our sample in, and we hit it with a whole bunch of energy. That energy will eject electrons from our molecule. That makes our molecule now positively charged. Those pieces are now floating around in the gas phase. Okay? As a positive charge, we then bend the tube, and it hits a magnet. What happens to the particles that were not hit or not ionized? They go straight. They impact the magnet and stop. What happens to the particles that were charged? They can now separate, get bent around to a detector, okay? Or actually really not just a detector. They go through a system to separate them out based off of their mass to charge ratio, okay? And then we then detect. Did a particle hit me? Yes. Okay? 2 seconds later, a particle hit me. Oh, 2 seconds means 2 mass units. So we see a bunch of peaks for how many times that detector got hit. That corresponds to the mass of your particle. We take our molecule, we hit it with an electron, and it generates pieces. Okay? So I could have gotten 3 possible pieces out of this. Everybody goes, well, how do you get those 3 pieces from 1 electron hitting it? Conservation of mass, that doesn't add up. we're not talking about one molecule turning into all these pieces. We're talking about billions of molecules being tested. Each of those billion gets hit with an electron, generating a new piece. That piece flies down the detector. The pieces get formed based on their most stable form. Okay? We take a bomb, blow up a car, we will be able to reverse engineer where the bomb was located. There's forensic scientists that do that. Guess what you are doing with mass spec? That same process, sort of. Okay? I do not expect you to get into the nitty-gritty details of it. It's ultimately coming back to the stability of a carbocation. Okay? Gets into reactivity. We won't worry about that on this exam. Oh, come on. What you need to be getting out of the mass spec, the peak furthest to the right, the tallest one there, that is the molecular weight of your compound. Big importance. Okay? You can use that to determine your molecular formula. With your molecular formula, you can determine unsaturation, that's double bonds and rings, that's super exciting stuff. Okay? If the molecular weight is odd, we know it's nitrogen. Okay? If we take a look at that tallest peak and we add 2 units to it, we say, is there a peak there? Is that peak of equal height? That's bromine. Is that peak 1/3 the height of my molecular ion? It's chlorine. Do I have a signal at 127? Then iodine is there. The other thing for iodine, is it a massive mass? Then it's iodine. Okay? That's all I expect you to get out of it. Okay? Very quick, process through fast. Okay? Fragmentation patterns. Maybe we'll talk about it next semester if we need to. Okay? If you're a more advanced organic class, there are more advanced ones. They look at fragmentation patterns. You're not expected or responsible for analyzing those. You can do it. It's just looking at the pieces. Okay? Now that I have a piece, where could it possibly have come from? So it's doing the same kind of thing. Which puts us into NMR, not mass spec. So we're deep into 16 now. What 16 is looking at is that every single atom has a magnet associated with it. Okay? Or not every single atom. Certain atoms have a magnetic field associated with them. The 2 most common atoms that have magnetic fields associated with them are carbon and hydrogen. Hence we have carbon NMR and hydrogen NMR. So what's happening is we're taking our sample, dropping those mini magnets into a large magnet, and seeing how they respond. Okay? Depending on what those magnets are near, they will respond differently to the external magnetic field. Which means we can then draw information about their structure out of it. Okay? So it's a neat little process, one that I will try to spin through as fast as I can on Monday. You have the basics of it. The more complex aspects that show up in the slides on Spectra, on NMR, I will not test on. Okay? I might make them extra credit, but I won't have explicit test questions on them. Okay? Nomenclature, you are for sure responsible for. That will show up. We'll talk about it in more detail on Monday. Hopefully that'll be more I have a question on this. Help me with this. And that's what we'll work towards on Monday. The exam is Wednesday.